Heads-up Experience, or HUX, is an AI system designed to revolutionize human-environment interaction by tracking eye gaze, analyzing the environment, and interpreting verbal contexts to capture and enhance multimodal data. This comprehensive approach enables holistic context interpretation and memory storage in real-time task-specific situations, facilitating more natural, empathetic, and intelligent interactions between the user and HUX AI. Intended for deployment in smart glasses and extended reality headsets, HUX aims to become a personal and useful AI companion for daily life, integrating digital assistance with enhanced physical world interactions. The evolution of human-computer interaction to human-computer environment interaction is critical, focusing on enhancing input and output modalities in personal smart devices. HUX AI is designed to realize these principles, deploying custom setups, smart glasses, and extended reality headsets. The system understands and interacts with the user's environment, making it a key component in next-generation personal smart devices. Key concepts include task of interest, objects of interest, events of interest, real-time video analyzer, multimodal context processing, and region of interest. The real-time video analyzer uses computer vision models to detect objects and events of interest within a video feed, providing insights into the sequence of events and their impacts. Multimodal context processing involves feeding multimodal data into a large language model to generate context-aware answers, enabling the HUX AI to understand and respond to user needs effectively. Improving human-computer interaction to human-computer environment interaction in personal smart devices is crucial, enabling humans to interact more efficiently with both digital and real-world environments. The HUX AI and its associated technologies have the potential to revolutionize how we use and interact with personal smart devices, making them more intuitive, responsive, and integrated into our daily lives. The paper proposes a novel approach to enhancing human-computer environmental interaction, HCEI, through the deployment of transformer-based language and vision models in extended reality headsets or smart glasses. This user-centric AI system, HUX AI, aligns its perception with user perception data, reducing friction in human-computer interaction, HCI, and minimizing the need for human articulation. The HUX AI system is designed to build on selective attention theory, video processing, merits of visual enhancement in extended reality, embodied AI, and multimodal HCI. The comparative analysis delves into various models of selective attention, including broad-bent filter model, Treisman attenuation model, Deutsch and Deutsch late selection theory, and Levy load theory, refining our understanding of human information processing. By understanding human information processing, the HUX AI system can be designed to reduce cognitive load, allowing individuals to focus on their primary tasks effectively and improving overall productivity. In video processing, the HUX AI uses events of interest, EOIs, based frames, leveraging deep learning models such as YOLO to analyze real-time video and extract EOIs using objects of interest, OOIs. This method enhances the signal-to-noise ratio, reducing computational cost due to the Vision Language Model, VLM, thereby increasing efficiency. Visual enhancement in extended reality is achieved through holographic labeling using AR algorithms and deep learning-based algorithms. Embodied AI systems such as Humane Pin and Rabbit R1 utilize VLMs to enhance human-computer interaction, HCI. The HUX AI uses VLMs to understand dynamic scenes in HCI environments, similar to the approach demonstrated in AutoRT, where VLMs are used for scene understanding and grounding in robotics. Multimodal HCI is also explored, building on advancements in gaze-facilitated information querying systems. The HUX AI extends the concept of multimodal querying into a dynamic and real-time task-specific environment, incorporating active change detection, real-time environmental adaptation, and personalized context memory. This approach addresses identified challenges, particularly in enhancing human-AI collaboration and improving decision-making processes. Here is the combined summary of pages 912. The research focuses on resolving query ambiguities and adapting to users' situational context in human-computer environment interaction, HCEI, by integrating multimodal features and gaze-enhanced information retrieval systems. This approach extends previous work by deploying it in a real-time test environment with continuous changes, allowing for dynamic testing with multiple questions involving different modalities within the same environment. The goal is to create a personal digital assistant (PSD) that enhances user productivity, decision-making, understanding, and task-specific scenarios in diverse environments, ultimately boosting productivity in real-world environments. The future utility of a general-purpose AI is decided by the number of domain-specific tasks in which human-AI collaboration is possible. HUX AI integrates a generalist base with modular, task-specific layers for flexible and specialized applications, as illustrated in Figure 2 and outlined in Table 1. The HUX AI agenda aims to ensure expertise in primary tasks, promoting regular use and proficiency in multiple daily tasks, enabling broad applicability throughout the day. The AI utility of a device is measured by the number of domains it can operate in, multiplied by its performance in each domain-specific task. In a task-specific environment, three key properties are observed: objects of interest, OOIs, events of interest, EOIs, and environmental context, EC. The desired features of AI for varied usability include spatial and temporal real-time scene understanding, tracking only EOIs and OOIs confined to a task environment, and understanding user perception using eye gaze data and enhancing visual perception using AR or deep learning algorithms. Contextual interaction using multimodal data enables the AI to assist users with real-time queries, suggestions, and answers. The heads-up experience HUX system integrates user perception and optimizes it for human-AI collaboration, handling real-world or digital environments. The heads-up experience HUX integrates artificial intelligence, AI, into smart glasses, extending the concept of a traditional heads-up display, HUD, by emphasizing an immersive, interactive, and multimodal interface. This AI system, also referred to as HUX AI, enhances user engagement with their surroundings in a dynamic and contextually aware manner. By consolidating functionalities typically managed by separate devices, HUX AI eliminates the need for smartphones and other gadgets, allowing users to perform a wide range of actions, access information, and interact with their environment directly through the heads-up interface. The HUX AI architecture, depicted in Figure 3, consists of integral components that manage data flow, processing, and modalities. Input data modes are converted to text captions and descriptions, integrated by the multimodal context processing engine using a prompt architecture. The creation of a new voice file triggers a multimodal context processing episode, collecting the latest scene captions stored in the last and only used LiU stack and retrieving the latest ROI caption whose origin image is created simultaneously with the speech audio file. The system's modalities include user speech input, eye gaze information, and other inputs that trigger multimodal context processing instances. These components work together to provide an immersive and interactive experience, enhancing user engagement with their surroundings. The HUX AI architecture, as depicted in Figure 3, is a multimodal system that processes data through various stages including origin, processing, context processing, and output generation. This architecture utilizes a LiU stack, or last and only used stack for efficient data handling. Page 16 details the components of the HUX AI system, including a real-time video analyzer, vision language model, large language model, and multimodal contextual memory. The real-time video analyzer detects task-specific events of interest, EOI, and out of interest, OOI, in real-time video feeds, extracting frames as needed. The vision language model converts input images into captions when required. The large language model serves as a multimodal data context processing engine and is also used for generating language outputs. The multimodal contextual memory stores contextual multimodal data for long-term retrieval. Figure 4 illustrates the temporal flow of frames from a real-time video feed, with green boxes indicating filtered EOI frames detected by the real-time video analyzer. These frames are sent to the vision language model for captioning, and the event data combined with image captions are then processed sequentially with metadata. The data from selected frames triggered by certain events are updated in the context window. EOIs can be obtained from real-time video of the environment through changes in the number of objects of interest, changes in object behavior, or custom-defined events specific to the application domain. This includes detecting gestures, actions, or environmental changes. Overall, the HUX AI system is designed to efficiently process and analyze multimodal data in real time, providing a robust framework for various applications requiring advanced AI capabilities. Here is a combined summary of pages 17-20. Real-time event-based video context processing using vision language models, VLMs, is illustrated in Figure 4, where detected events of interest are processed in real time. However, Figure 5 highlights the reality of this process, where some events are missed due to the computation time of the previous frame. The VLM computation time spent processing the previous frame results in subsequent events of interest being missed until the VLM is freed. To address this, a hybrid approach is proposed, where the VLM computation time is utilized to export events of interest as frames, and the event data from the real-time video analyzer is sent to the context processing engine to reconstruct the temporal scene textually. This enables the context processing engine to understand occurrences in real time while saving significant computing and processing time. During VLM processing of a frame, multiple frames might get classified as events of interest. After the VLM completes processing the current frame, the middle frame is skipped over to focus on the latest frame, ensuring the real-time video analyzer provides essential event data to the context processing engine. The proposed hybrid approach leverages the strengths of both VLMs and context processing engines, enabling efficient processing of real-time video data and reconstructing the temporal scene textually. This method enhances user perception and task-specific scene understanding by identifying and processing events of interest in real-time video streams. Task-specific scene enhancement is achieved through repurposing the same computer vision model to filter out events and annotate the scene image feed with objects of interest relevant to the user's task. This approach offers several benefits, including improved task-specific selective attention and awareness of the scope of task-specific objects of interest. The authors acknowledge limitations in future work, including the potential for improved techniques for mental recovery and focus renewal in the scene, and emphasize the importance of dynamic shifting of focus based on changing environmental priorities and intentional disregard of non-essential information for the task. Overall, the paper presents a novel approach for enhancing real-time video context processing and user perception, with significant implications for various applications in computer vision and artificial intelligence. The research paper discusses the modularity of task-specific computer vision models for enhancing user visual scenes in augmented reality applications. It illustrates how different computer vision models detect and label objects of interest in various scenarios, facilitated by agentic behavior. The system understands context and decides when to utilize specific models without explicit user input. The user's visual scene is enhanced by the chosen model, providing a visual aid through labeled objects of interest. The paper also outlines the eye gaze processing pipeline, demonstrating the parallel and interdependent nature of gaze and scene processing. Eye gaze data is used to segment the region of interest from the scene, which is then used by the vision language model to generate text inferences. The process translates this data into textual form, combining it with the VLM's outputs. This combined data is stored in a structured multimodal memory format, which can be retrieved later using contextual cues. The paper concludes with the data structure of a multimodal contextual memory, highlighting its relationship with other memories. The research introduces a novel multimodal contextual memory pipeline that enhances human-AI interaction through efficient data storage and retrieval. This pipeline utilizes a unique data structure for storing images, captions, and contextual information, enabling the system to minimize computation costs during future queries. The system's capabilities are demonstrated in solving the selective attention problem in real-time human-environment interaction, where the AI focuses on tasks outside the scope of human selective attention. Enhanced situational awareness is facilitated through the HUX AI system, which improves detection of subtle environmental cues or threats in complex scenarios. Additionally, cognitive offloading is achieved by monitoring less salient task elements, freeing up human cognitive resources for higher-level decision-making. The AI system also provides enhanced multitasking support in complex scenarios requiring attention to multiple subtasks. In the spatial and temporal scene recall experiment, the HUX AI computer vision analysis is compared to manual video analysis, showing general alignment but some discrepancies. The system utilizes selective real-time data computation, storing all data without real-time computing and computing only when necessary. In the task-specific scene perception experiment, a multimodal task-specific scene perception is demonstrated using AR algorithms and deep learning computer vision algorithms. The visual language model, VLM, is used in image captioning of the enhanced scene, leveraging LLM-based agentic behavior. This research highlights the potential benefits of this technology in enhancing human-AI interaction and improving task efficiency. In a printed circuit board (PCB) scenario, a user inquires about components and defects, and an agent utilizes the PCB HUD tool, equipped with a PCB defect detection model, to identify and describe 3 mouse byte defects via visual language modeling (VLM). The agent explains the defects, drawing from task scene knowledge enhanced by a task-specific computer vision model and a large language model's trained knowledge. When the user requests more information, the agent accurately recalls the defects, reiterating their spatial locations. The conversation is summarized in Table 2, illustrating the agent's use of the PCB model to detect defects, receive a labeled image, and explain the imperfections in the copper foil. The agent maintains accurate knowledge throughout the conversation, correcting potential misunderstandings. In a separate scenario, the research focuses on creating multimodal contextual memory, demonstrated by the HUX AI system remembering a new engineer, Imam. The agent captures a scene image, extracts relevant information using conversation context, and stores it in a multimodal contextual memory. Figure 12 illustrates this process, showcasing the scene image and the extracted region of interest. Table 3 provides a detailed demo of the stored memory, highlighting Imam's attributes, such as appearance, setting, and objects in the scene. The context includes Imam's position, clothing, and demeanor, as well as the lab's workspace, including shelves and electronic components. This multimodal approach is crucial for AI systems to understand and recall complex scenarios, emphasizing the importance of contextual memory in human-AI interaction. The research on HUX AI focuses on selective attention, drawing inspiration from psychological assessments. It explores the ability to pay attention to multiple things the user is not, aiding in real-world stochastic situations. The system helps verbal recall of objects by having conversations about overlooked items. The experiment setup involves a dark background with objects of interest as fruits, and the system's observational capabilities are restricted to increase the signal-to-noise ratio. The goal is to dynamically change the environment by adding or removing fruits, while the user interacts with the AI, asking questions about the environment using eye gaze. The test aims to mimic any environment, and promising results could be applied to other environments. The experiment uses a single user, and the system's usefulness is tested through various types of questions, including those that involve multiple modalities. The hardware used includes 3 independent systems networked together for computation. The Human User Experience (HUX) AI system is designed to enhance human perception and reduce cognitive load by processing multimodal context from user prompts, gaze, and speech in real time. It receives raw eye of interest (EOI) frames, processes them, and sends them as image captions to System 3. The system is divided into 3 parallel systems for deployment efficiency. User interaction involves pressing the spacebar to input voice commands while the system captures the gaze image simultaneously. Trials noted errors in speech-to-text conversion and instances where the user's gaze was outside the scene environment. The multimodal context processing prompt architecture consists of 4 components to answer questions based on previous responses and new multimodal information. The system can overcome issues in selective attention by retrieving data from HUX AI memory when prompted, reducing cognitive load and improving quality of life. Although the current prototype has latency issues, future versions can address this. The HUX AI enhances scene perception, facilitates interactive questioning, and enables informed real-time decision-making. The research discusses the development of an AI system capable of creating multimodal contextual memory and retrieving it through contextual cues. This system integrates multiple data types, enhancing memory recall and decision-making. The efficacy is demonstrated in experiments involving human-AI interaction within complex environments. Figures 14 and 15 depict the experiment setup, showcasing the AI's ability to capture and store scene captions in real time. However, the current implementation has limitations, such as the need for testing in more environments and the loss of scene data in real-time interaction. Future works include assessing multimodal memory retrieval capabilities in large-scale data and considering privacy limitations. The system, known as Heads-Up Experience, HUX AI, is designed to revolutionize personal smart devices by enhancing human-computer environment interaction. It can integrate with various technologies, such as wearable robots, drones, and smart appliances, to provide seamless control and interaction. HUX AI can navigate GUI environments, process multimodal data, and support creative endeavors like brainstorming. Its ability to store contextual, multimodal memories enables the fusion of diverse data types, aiding in problem-solving processes. HUX AI is a groundbreaking framework designed to enhance human-AI collaboration through multimodal interactions, leveraging eye gaze, scene analysis, and speech input. Inspired by language models capable of few-shot learning and higher-order theory of mind tasks, HUX AI aims to revolutionize personalized intelligent technologies. The concept of attention plays a crucial role in understanding the HUX AI framework, with research on selective attention highlighting the importance of perceptual load in filtering out irrelevant information. This concept is particularly relevant in object detection, as demonstrated by the Yolov-7 algorithm. Furthermore, the introduction of GPT-4o has also influenced the development of HUX AI. HUX AI has applications in various domains, including mixed reality, as demonstrated by the Microsoft HoloLens, and robotics, as shown by the AutoRT embodied foundation models. Additionally, the concept of gaze-facilitated information querying, as explored in G-Voila, has contributed to the development of HUX AI. Advancements in multimodal models are also discussed, focusing on the gap between current open-source suites and commercial models. The authors emphasize the need for scaling up vision foundation models to align with generic visual linguistic tasks. They highlight the importance of object detection models and datasets for achieving this goal. The concept of retrieval-augmented generation for knowledge-intensive NLP tasks is introduced as a key methodology. The role of aerial grippers in robotics and visual language models for GUI agents is discussed, concluding with the need for synergy between different technologies to achieve significant advancements.